Good afternoon. Any questions?
This kind of information are kind of confusing right now.
That's a statement. Any
Yeah.
questions?
We have questions on that, but I don't know when is the right time.
I'm sorry?
I don't know when is the right time. Which question are you talking about?
We have some questions on the
Continuation.
type sheet.
Right. All right.
So
Let me pull it up.
yeah.
What's that continuations for?
Yes.
Yeah.
So the sixth or seventh line it says when K can return from the ship, then B must be a subtype of C.
Right. So the question was, when the whole reset expression here has some kind of a value, that could happen, right? You would say, val x equals, and then assign the reset to it. So the question is, how can it type the reset? And maybe I'm wrong. So there's two possible exits, right? You can exit out of the reset by exiting from the shift,
Yes.
and you can exit by popping out of here.
Yes.
So I'm going to have to look into this. So naively I said, well, that means that one of them has to be a subtype of the other, right? But now I'm no longer so sure now that you ask, because maybe what it simply does is it computes the least common type. I'll have to look into it. So it's the same situation when you have like an if and an else. These things could have different types, and then it takes the least common type. It's possible that it does that. I have to so put a question on Piazza, and I'll answer it. But that's an excellent question, because I remember as I was trying to explain it during the lecture, I was like 30 seconds ahead of what I was going to say, and I couldn't explain it, so I just omitted it. But I had a funny feeling about it. Because how would it know which direction it goes? So I'll look into it.
Okay.
Good question.
And the other one, iterate CPS param.
Yes?
So we have a question about when to use iterate CPS and iterate CPS param.
Okay, that one I can explain. So you can always use CPS params, nothing wrong with it, but you can use as a shortcut, if it's BB, then you can save yourself 7 letters, 8 letters by using CPS. It's just a shortcut.
Okay. So please find the place and changes in the tree walk program which is given in the slide.
Yeah?
Next few slides we have.
So
This one?
let's right. So in the shift, after K1 is equal to K statement,
Yes?
if we had a statement which returns an integer,
Right.
then my
Okay,
annotation would be
So let's have a somewhat more natural thing, right? It doesn't really make sense to return an integer, but we might want to return a file. We might want to return the file object that we've encountered, right?
okay.
So if over here we return the file,
Right.
then this would have to become CPS param, I guess.
Right.
And one of the two, I can't flip back without losing my letters. Which one is this one B or is this one? This one is B, right?
Right.
So presumably this one then would become file.
the
Oh,
type of
oh no. If we are returning the file
Yeah?
F inside the K block immediately after the K1 equal to K statement.
so that would be the
Not
type
after
Right,
the
so that's what I
previous
meant.
line.
Here.
Right. So that would be the type of
reset.
B.
No, it's
no.
type
See, I can. That's why I say I can't remember. Okay, then it goes. So you said C is this one and B is this one.
Correct.
Yes.
Okay.
Correct. So that would be unit
Comma file. Yeah.
Then you have to change everywhere the same thing, right?
Yes.
In all the annotations.
Yes.
So when we did that, we returned an int, so we made it a
Yeah.
unit comma int. it gave us an error saying,
Okay, I would have to see it. You're just gonna have to post the code.
okay, And
There's
in
no
that-
way I can figure that out by just looking at it.
right.
Yeah.
So in that case, your C is basically 5,
That's true. It should be right.
and your B is
You know, it's a little bit iffy whether B really is unit or not. What you may have to do is, just to be on the safe side, put in a unit here
so then
and see if it picks it up, because it might otherwise look at the type of shift and say that's the last thing that happens, and it yields a file. And it sometimes is really prissy about these things, and I can't quite figure out when. So try to put in the parentheses here, and if that does not work, then post it, and I'll have to look at it in slow motion.
Okay, because in this case, as we understood, B was unit and C was 5. So the
Right.
B must be a subtype of C. The earlier
Well,
one.
and I hear you. I'm wondering about
That gave an error.
the
actually.
subtitling myself. So I think you're onto something there. Put these questions on there with the code that doesn't work, and I will get back to you. I mean, it's impossible for me to do this in real time. Yeah. But these are excellent questions, and what you're doing is exactly what a pro would do to take something that kind of works and kick the tires and make it a little different and see what happens. Other questions? Yeah.
Internet access.
Um,
I don't know. Yeah, don't worry.
no one has internet access?
So there's some issues, back issues with that.
You have? Okay. Well, then,
How do you connect?
So another sentence is
okay, other questions?
gets
Other questions? Other questions? All right, then let's get going with the concurrency lecture. So, just out of curiosity, who is basically familiar with the standard Java concurrency structure, meaning the object locks, wait, notify, that kind of stuff? Anyone think that they're comfortable with that stuff? Nobody is comfortable with it. All right. So then I might as well go through it in slow motion. So we all know why we care about concurrency at this particular point. We've always cared about concurrency. I mean, concurrency was always important. But it was mostly important in the traditional days, like when you have an operating system, or when you have a web server, or when you have a graphical user interface system. Concurrency on a single processor system was important for liveness, so that different parts of the different tasks all had a chance to run, instead of one running and starving out all the others. Now we're entering a world where we're going to get more and more processors, and we're going to have the opposite problem that, sure, we could probably now give every little bit of activity on the computer its own processor. We could have, for each task that runs in parallel on your machine, when you just run ps-a and you get right now maybe 50 concurrent tasks, pretty soon we'll be in a position where every one of them can have their own processor. You'll have 64, 128, 256 processors on your chip, if we can cool them at least, and there's not going to be an issue with that anymore. The issue is going to be, how do you keep them all busy? Now you've given every easily identifiable task a processor, and you have another 100 processors to go. What do you do with them? And so that's going to be bedeviling us more and more. And so we will have to find a way of structuring our programs so to distribute the workload over the available processors. They're not going to get any faster. We're just going to get more and more of them. So I was at this conference last Tuesday, and just about every single presentation, that's what people were talking about. That they're worried about this problem. They don't know what to do about it. And they came up with kind of partial solutions. There was one guy who said, we're having all of these processors pretty soon, more than I know how to make use of. And so I'm writing this program, and it's not actually going to work right. There's going to be some race conditions, which we'll see today in the lecture. And it's really difficult to correctly reason about them and to make them all go away. But maybe it doesn't matter. Maybe if the answer is close enough, maybe there is a set of algorithms where this is okay. And so he was then looking at some such algorithms where if he can kind of cleverly structure the algorithm where the mistakes were bounded. So he had stuff that, and he says, that's how we were. Our DNA isn't perfect in any way, and mistakes happen all the time, but they're kind of self-correcting more or less. And yeah, you die after 70 or 100 years, but that's an eternity. So that was kind of an interesting twist at it. But most of us would not be very happy with following that approach. When you have your bank account balance is at stake, and you don't really want to have that occasional error that deprives you of $1 million. Even if maybe the chances that you have the occasional error that goes the other way around and that gives you $1 million, it's not something that we kind of enjoy having in our bank account. So we kind of want to have correctness, and we want to have concurrency, and programming languages are poorly equipped for that. So to see a language that does this really poorly, we're going to look at Java. And so the tragedy is when Java was created, it was explicitly created to be one of the first languages out there that did a good job with concurrency. And it did a good job for concurrency 20 years ago, and so now it's slipped out of its grasp. So we're going to be using Scala syntax so that those of you who have forgotten Java don't have to remember it, but we're going to be using the Java concurrency primitives. So to create a thread, you have to give it a runnable. A runnable has a single method called run, and inside there you put whatever it is that you want to run in a separate thread. Then you call store in the thread, and that's the end of it. A thread can call thread.sleep if it has nothing to do. That's not usually a kind of problem that we're going to be having, because our threads we want them to have plenty of stuff to do, but they could. So in the old-fashioned way, the thinking was, thread has to call sleep all the time, because otherwise, it's going to be too busy. But nowadays, we're happy if the thread is busy, because we have extra processors that it then could also be kept busy. All right, so now the complicated part comes when multiple threads access a shared variable. And this, of course, happens all the time, that if you have all of these threads that can work in splendid isolation and not affect each other, that's nice. But that doesn't often happen. Usually when you work on a problem that needs to be cut up into smaller problems, there's some shared data. And so we call a race condition a condition where the outcome depends on the arbitrary scheduling of threads. So the traditional example is the following, where you have a set of deposits and withdrawals on a bank account, and that access the same balance. So over here, I'm having a bank account, and I'm having a deposit method here, and I'm having a withdraw method, kind of what you would think. And over here, I'm running a couple of threads. These threads here, they all deposit into the same account. There's a single bank account here. And these ones here, they withdraw from the same account. And that's pretty much what I do. See if I have the printout here. No, I don't. So I actually have to run it. Hang on. Program called test. Oops, I didn't have a new line here somewhere. Okay, this always happens when I you run it a little longer. We have a few more threads. And where did I print? Change the prints to print on. Oh, I see what I did. And I don't think I even need this many. So here I've ran a whole bunch of them, and at the end my balance is 0, which I kind of want it to be at the end. Because I'm depositing and withdrawing the same amount of money. But if I play with this, after a while I'll be able to get my balance to be non-zero, I hope. Yes. And so now I've withdrawn and deposited the same amount of money in a whole bunch of threads. But this time it worked out in my favor. I ended up with $24,600. That's nuts when it happens like this. It could go the other way around and I could be losing money in the game. So why is that? Why is it that sometimes I just gain or lose money? And so we have the shared data. And so when we look at what happens here, I'm not sure the flow chart's on there, I'll just draw it. So I have a variable balance. And that started out with, let's say it was 0. And now the first thread here would come along and it deposits $100. So it has a local variable called new balance. So this is the shared variable here. The new balance here belongs to only this thread, and it's now initialized to be balance, which was 0 plus amount, so it's 100. Now it can happen that right at this point here, for whatever reason, this thread here loses control. And this thread here starts cutting in. So this thread here will now compute the new balance as the balance minus amount. Balance is 0, so its new balance is minus 100. It then now updates the balance to be the new balance, so now the shared balance is minus 100. And now this thread comes along, and you don't see that here, but it ends up by saying balance equals new balance, which is its local variable, which now overwrites this thing with the 100, whereas one deposit and one withdrawal should have canceled each other out. They didn't cancel each other out, but whichever one happened to be later in storing its results won out. So it's a classical race condition that happens all the time when you have shared variables. Now, so that's the kind of thing that we want to avoid. The traditional way to avoid that is by using locks. And so the way to acquire to use a lock, the most robust way of doing it is you get one of those reentrant lock objects. So we're going to make ourselves a lock object, so that in the bank account. And then in the deposit method, we're going to call the lock method on this lock. Now, if multiple threads try to do this at the same time, only one of them will succeed. The first one, whichever happens to be the first one, will succeed, will acquire the lock, can then access the shared resources. Because none of the other threads that try to do the same thing is able to get past this point. We now know that this thing here is an exclusive access. And so as long as we make it so that everything that needs to be in a transaction, the reading the bank account balance, updating it, and saving it, as long as that's inside this protected region, we're okay. And finally, we have to remember, of course, to unlock the lock, because if we didn't, then we would starve all the other threads that try to get into this. So that's the basic coding pattern here. You acquire the lock, you do your exclusive stuff, you make sure that what you're doing here is an entire transaction, and then when you're done, you unlock. Notice that the unlock part here is in a finally clause. Now, that's important because if this code here happened to throw some exception, which it might. If this was actually doing some database access, for example, you might easily get a SQL exception. Or you might get all sorts of things. If this thing, for whatever reason, had a null pointer exception, say. And this might actually happen to the best of us, that accidentally we program a null pointer exception. Then at this point here, it's important that the unlocking happens anyway. Otherwise, pretty soon our program will deadlock. You'll be seeing some deadlocking programs in the lab. It's no fun. So that's the basic scheme. And if that was all, maybe things wouldn't be so bad. But it's difficult to do much progress when all you have is locks. So you can't even look at shared variables without locks. So here's a typical example. I want to withdraw some money, but before withdrawing money, I want to make sure there's enough money in the bank. Typical problem. So I don't, in this particular implementation of the bank account, it should be illegal to overdraw. So what do? I could, of course, naively do the following. I could say, what is it? What's greater than amount? So let's say that I did the following naive code here. In a multi-threaded scenario, this test is completely worthless. Because here I'm testing, do I have enough money? And right at this point, I know I have enough money. But now I don't know it anymore. Right? Because some other thread might have already withdrawn some money before I even exit the closing parenthesis. Right? So this test is worthless. So I have to lock. So right around here, so let's make it good. So I'm going to lock here. And then I'm going to unlock here. This is now fine. If in fact there was enough money in there, then now I'm going to be able to withdraw and safely. But what if there wasn't? I guess what I really wanted to is I wanted to wait. I wanted to say while there was not enough, do nothing, sleep. And then once the while loop says, oh, there is now enough money, then I want to go and withdraw. And I want to do the entire thing, of course, between a lock and an unlock, because otherwise the test is going to be worthless. Yeah, now no one can deposit anything. Right? Because I hold the lock on this thing. So that is the problem with locks. And to solve that problem, 40, 50 years ago, people came up with these condition objects. So there is this this other thing that you can do. You can ask the lock, say, give me a condition object, and then it gives you a condition object. You can call it anything you want. And so over here, what we're going to do is we're going to be locking. So this is inside a lock. The thread enters acquires the lock, makes the test, and it's now still inside the lock region. And now it finds that things are bad, it can't progress, and it doesn't want to exit the lock. Because if it were to exit the lock, then it would lose any significance of this while. So it wants to stay inside the lock region, but it wants to give some other thread a chance to succeed. And then it calls await on this condition object. That now means that the thread is parked in a special area, which is different than all the other threads that are trying to acquire the lock. So at this point here, the thread is blocked. It's put in a special area that waits on this condition. And now other threads can do their work. And eventually, this thread wants to, of course, keep on going, and it now requires on cooperation of other threads. Some other thread now has to call the signal all method on this particular condition. That tells all of the threads that are waiting on the condition that it's worth trying again. So at this point here, so we have thread number 1 calls lock. Thread now, and then it calls this loop here, so it now calls await. And now thread number 1 is just kind of sitting there doing nothing. Thread number 2 comes along. It also calls lock. And now this lock succeeds because thread 1 is no longer actively executing any code here. If it had been called a little bit earlier, if it had been called here, then the lock wouldn't have succeeded yet. But now the lock succeeds. The other thread then can do plus equals amount. Now the balance is a little larger. This amount may be a different amount, of course. It then calls signal all. So what happens when we call signal all? Yeah, it's a little subtle. Yes, this thread now becomes unfrozen, but
This will release the lock and signal.
not yet. It will not yet release any locks. So that's the subtlety. This guy here at some point is going to say unlock. And only after this guy said unlock will the first thread have any chance of succeeding again. So this guy keeps on going. And so starting at the point of the signal all, starting at this point here, this guy is now eagerly trying to again acquire the lock. But it's not going to succeed until this point. At this point, it will, maybe it has become the chosen one to reacquire the lock, and it can then continue on with saying balance minus equal amount, and then it too says unlock. So it's important to realize that what signal all does is it merely gives the next fellow a chance to compete again. Yeah?
So when you are saying away, and once it is unfrozen, you still have to acquire the lock
Yes.
again?
Yes. It has to. It competes with other threads to reacquire the lock. That's all that the unfreezing means.
Right. So the statement while balance less than amount, that statement is executed again.
Yes, absolutely. So where it comes out is it comes out after this parenthesis, then it hops back in the condition, and then it checks the condition again, which is after all what you want, because you have no way of knowing whether the balance is now sufficient. You know that the way that we've set it up, that it's likely to be bigger. So there is a better chance, but you don't know for sure that it's going to work. So that's another rule, that you should never put an if here. You should always put a while here. So that's the basic mechanism, and so it's a little bit confusing of what all of this notification scheme is. So the classic analogy here, all right, the classic analogy to explain this is actually a restroom stall. But when I do that, when I did that last time, the publisher made me change it to a phone booth. But it works so much better with the restroom stall. So the way it works with the restroom stall is, there's just only a single portable toilet, and there's a bunch of people who want to do whatever they do, and so one of them goes in and finds there's no toilet paper. And of course, it would be a bad strategy to simply stay in there to wait for that condition to change, because it would not allow the attendant to come in and change it, right? So that's where then the await comes in. So, and you don't just want to leave and give up, right? Because then what's your chance of getting back in? You're going to have to compete with hundreds of other people and so on. So that's when you call await on the insufficient toilet paper condition, and that means you can get kind of hang around, close to the entrance. You have a better chance of getting back in, hopefully. And so then the attendant comes in, locks the door, of course, so that he's not mobbed by all these other people, refills the toilet paper. Now at this point, then the attendant is going to say, all clear, but he hasn't yet unlocked. So you're already eagerly awaiting that you can get back in, but you can't quite get back in yet because the attendant is still in there. You have to wait for the attendant to leave, and then you can go back in, and you can pick up where you left off. You don't have to, to start everything completely fresh. So that's how locks and conditions work. Yeah?
So basically, the one who is awaiting is given the first preference.
Well, that's somewhat up to the implementation. One would kind of think that that's what would happen, but there's no. Everything will happen correctly whether or not that's the case.
So, what my question is, what is the use of having this await? And the normal lock and release method would also do the same thing, right?
No, because then at that point it would become much more random. Your chance of being able to make progress would then, eventually, presumably. Okay, let me put it this way. In that case, it would be possible to starve out a thread that does useful work, even though that's the wrong analogy with the with a bathroom stall, but with bank accounts, it's the right one, right? So the thread wants to make the withdrawal here, and it might be completely starved out because every time someone butts in and already withdraws more money. Whereas this guy here, they get back in where they already were. But I agree. If you simply were to say it's okay if some threads just never make any useful progress, then you wouldn't need that scheme.
So you're saying there's some special priority given to that because it was in a different pool?
It is in a different pool, and I would imagine a sensible implementation will in fact do that. So that's the basic scheme, and so what's wrong with it? I think there's two problems with it. One is that it's unintuitive to people when they need to lock, although that's still fairly clear. You lock when you need to have exclusive access to a resource, but people kind of don't like to lock, or they forget to lock. So for example, when you have a condition where, say, you have multiple threads checking the status of some flag, whether they should continue. You might have one thread that says flag equal true. And this is a shared variable. And then you have other threads that says if while not flag. So this is thread number 1, and this is thread 3, 2, 3. So they're kind of waiting for thread 1. Maybe thread 1 needs to do some computation, and it sets this Boolean to true. So at the outset it was false, and now when you look at some code like this here, it seems like you wouldn't actually have to need to use any synchronization. Because what could go wrong, right? The first thread here eventually is going to set it to true. And then these are guys sleep, they wake up again, and eventually they're going to find it true, and then they go on. It looks like this would require no synchronization. But the sad truth is, with a modern processor, if you try this out with no synchronization, it's very likely that these threads will sleep forever. So here we have no synchronization. And the reason behind that unintuitive behavior is that when you have multiple CPUs, and say T1 runs here, and T2 runs here, well, your flag, this is not really, my flag is here. So it goes first false, then later it's true. And you would say, well, T1 sees this flag, T2 sees this flag. Eventually T2 is going to see it. It's flipping from false to true. So what's wrong with the picture? Yeah, it's a RAM, right? It's a variable. The variable is in, there's no little memory to it.
It might go off the stack.
Well, the stack is memory. Okay. But you're close. So this is why they make you take a hardware class. So what's in modern life? It turns out that RAM is, what's wrong with RAM? It's slow. It is excruciatingly slow compared to the speed of a processor. It takes many, many cycles to get some piece of information from RAM into the CPU. It's unintuitive, but that's how it is. RAM is slow. And so it's one of the presenters at the at that conference, he was asked about this, and he was a hardware guy, and he said, you know, get over it. RAM isn't going to get faster anytime soon. It is so much cheaper to build it this way. It's just the way it is, and it's going to be like that for another 10, 20 years. And figure him being, you know, one of the world's most famous hardware guys, he knows what he's talking about. And so RAM is just slow. And so what the CPUs do is they do have a small amount of faster cache memory in here. And so they'll take the most recently read variables from RAM and cache them. You know, just like what you learned in yesterday's operating system class, where RAM was used to cache the disk, you know, which is, of course, you know, incredibly, interminably slow. Now one even needs to have something that caches the RAM. And this happens all the time. And your processors do that, the ones in your laptop. So when you when you write code that accesses a flag like that, there's a good chance that this guy and this guy, each of them have a copy of this Boolean inside their cache. Now, if you don't put the word, if you don't do any synchronization mechanism, if you don't use any locks, then the optimizer will have no idea that you access these variables from multiple threads, and it will not synchronize the caches. And so in that case, this guy here will fetch the thing, it's false. It'll not synchronize, it'll always think it's false. This one here will, of course, update it, but it'll not tell the other CPU. If you make an access inside a synchronized block where you have locks, then everything is fine. Then the caches are told to talk to each other about these variables. And the optimizer says, look, there's these 5 shared locations that are accessed inside this critical section. Make sure the various caches do talk to another. And so it's unintuitive. And it used to be, just a few years ago, when I was talking about this, no student would believe me, because it worked on their machine. And so I count myself very fortunate to have seen the time during my teaching career that every student now has a multi-core machine, because now you're going to see it just as much as everyone. So a few years ago, it was the hardest thing to convince people that this was actually happening. And now you'll see it right away. It just happens all the time. So technology is wonderful. So it's unintuitive. And you really have to force yourself to win every piddly little thing that can be accessed by more than one thread. You have to identify them all. You have to make sure that you do your locking right. And then you do all your locking right. Eventually you get to the point where everything is beautifully locked, and there's never going to be a situation where 2 threads access the same resource outside a locked area. And you run your program, and you look at it, and you look at it, and you look at it, and it has deadlocked, because one thread is waiting for the other, which is waiting for the first. And it's very easy to create those situations. There's been, for 50 years, people have been trying to come up with some way of identifying and breaking deadlocks, and no one has a good way of doing it. So deadlocks are very common, and you'll see a few in there. So anyway, none of this stuff is new. So this was all done in the 70s by Hansen and Hoare, and they in fact did it with a precursor of what now would be called classes. And so they made it so that a class that can be shared, whose objects can be shared amongst threads, they call them a monitor. I guess because they look like these lizards, I have no idea why it's called a monitor. So they call it a monitor. All fields are private. Each object has an associated lock. All methods are automatically locked, which makes sense. So that way, you must go through a method. The method automatically locks, so it's never possible for 2 threads to access the private fields at the same time. And then you can have conditions. And then they gave some syntactic sugar for this. I'm kind of give you a flavor of what this might look like in a modern language. They would have a keyword monitor for a class like that. Every field was automatically private. Every time that you have a method, it automatically has a lock. You don't even have to write them. And with those constructs, then they made it into a programming language, and that was kind of the first concurrent programming language at the time, called Concurrent Pascal, and it worked fine. So the Java people, of course, knew about that, and so then they had a feeble ambition to imitate the monitor construct in Java, and they botched it mightily. So here's what they did: is they said, well, we don't really want to have every class be a monitor. That would be too restrictive because locking is slow. So they said, if you want to lock, then you have to use this synchronized keyword. They did give every object a lock. So actually, to this day in Java, every single object in Java has an intrinsic lock. You don't have to call the reentrant lock thing in theory. You could just use the intrinsic lock that the class has. And it has one condition object. You get those for free. Of course, it's optimized the way that those locks and conditions only manifest themselves in the virtual machine in the very rare case that you actually need it. So to have a method that automatically acquires and relinquishes the intrinsic lock, you use the synchronized keyword. So it, when you enter, it acquires the lock. When you leave in any way, even by an exception, then it releases them. Then you can call notify all on the object itself, which then calls notify all on the single condition that you get from it. So wait and notify all are methods in object. You may have seen them in the Java docs, that they operate on this one intrinsic condition. You can do even more than that. You can have the object lock on a particular, you can take an object which has a lock and you can say, I want to lock that lock. And you do that with the syntax, synchronized, the thing that you want to use as a lock. And then inside here you do some stuff. When you enter the block, the lock that belongs to an object is acquired. When you exit the lock is given up. So you can do kind of the same thing in Scala. You can take an object called synchronized and then you give it a block and it acts the same way. So Scala doesn't have the concept of synchronized methods, but it does have this one kind of Java-like way of doing synchronized. Now the good thing is you should not use it. First of all, no one understands it. People are forever confused about what exactly does synchronize do, what exactly do wait and notify all do. The advantage of using the explicit objects that I had in my slides here, the guy here, and then the conditions on the next slide. Here. Ones here is, you can see them. You have to make them with your own hands. You call methods on them. They're there in your face, and it becomes pretty clear what they are. The ones inside the Java object model are hidden. It is perfectly unintuitive. The other thing is that it doesn't even work. So because you would think that when you use these, you would get kind of the same effect that you get with the monitors from the 1970s. But of course, in Java, there's no requirements that fields are private. You can make a class with some synchronized methods, with some non-synchronized methods, with some public fields, with some private fields, and you get no guarantees at all. At that point, you get something that is that is quite unsafe. And here's another thing. So let's say that you use this intrinsic lock. Let's say, so I have the synchronized deposit method. Synchronized means that if I have a particular bank account B say, and I call b.deposit, that B sitting inside has a little lock. I don't know how to draw a lock. I'll give up. Here's my lock. So, so B has a lock, and when you call deposit, because it's called synchronized, as soon as you enter the method, it gets locked, and then later it gets unlocked. But the thing is, anyone out there can grab B and also write, and people do this, people can write synchronized B so they can grab your object, lock on it, and go to sleep. And this way they can deadlock your system. So you have something that is insecure and prone to deadlocks. So the designers of Java managed to take what was a perfectly reasonable architecture that was invented in the 1970s and then turn it into something that was insecure and dangerous. And so in 1999, one of the inventors of the original good stuff wrote this article where he reviewed this, and he ended with, "It is astounding to me that Java's insecure parallelism is taken seriously by the programming community a quarter of a century after the invention of monitors and concurrent Pascal. It has no merit." And indeed, it has not. So this is what always happens when people design a programming language and touch stuff that they have no business touching, and so this was the case here. They didn't take this very seriously. They definitely were better than just about anyone else out there. You know, it's taken C++ another 20 years before C++ started worrying about concurrency, which they now finally have in 2011. But it was just not very good. So the other moral here is that don't use synchronize unless you really know what you're doing. If I see anyone use synchronize, I will spring a little quiz on you to demonstrate to you that you don't know what you're doing. I did that with the students in Vietnam because they kept using it, and they learned otherwise. All right, so easy lab. Run this program. Find bad things happening, fix it, use a lock, and then we'll have a little exercise that makes a deadlock so that he doesn't see it. And then if you have time, there's one with another deadlock. Let's see how that goes.